and I will I will give a talk about research that I was working in the last 3 to 4 years, and it's based on cooperation with multiple colleagues and friends, and it will have two parts. First will be the methodology, where I will explain something about robust Bayesian meta-analysis, and this was mostly based on the work with Max Meyer, E.G. Wackermakers, Daniel Quintana, Chris DeCalagis, and Tom Stanley. And then later I will talk about applications and some examples. And this was based on work with many more people. And we'll see how far we get through the methodology to the examples. And probably a good disclosure from my side. I'm not a statistician, I'm a psychologist. I will make a talk kind of high level, and I will be talking mostly about I will be very conceptual, but I have one-sided equations. So if you are here for the equations, I can wake you up when the equation slide comes up. You can look at them and then we can continue and be all happy. So I'm not sure how familiar you are with meta-analysis and publication data, so I will just give a quick overview on that, and then I will talk about the methodology that we developed. And so first, the meta-analysis, which are basically the common way how to combine evidence from multiple studies. And if you have the usual pyramid of evidence, where at the bottom you have case studies, case reports, and you have observational studies, etc., then meta-analyses are usually at the top with systematic surveys. Yeah, and some people also put opinion papers on top of that, because if you are famous, who cares about evidence, right? And then I will talk about publication bias. So just very quick overview of meta-analyses. There goes to combine evidence across multiple studies, and it's usually some type of a weighted average. And the different methods for meta-analysis differ in the way how they weight the estimates from different studies. So if you ever seen a meta-analysis, you have probably seen a figure like this, which is called the forest plot. And in the forest plot, you have estimates from individual studies. So here you have 1, 2, 3, 4, 5, 6 individual studies. Each of them provides an effect size estimate and a confidence interval. And the goal of meta-analysis is to combine the estimates into some pooled estimate and some estimate of uncertainty. And of course, you can estimate and you can also test for the effect. So this is usually the main goal of meta-analysis. And you can also quantify between study heterogeneity and etc. So, and the two most common ways how to achieve this pooling of evidence are fixed effect models versus and random effect models. And I will just slightly touch upon them, so you also have maybe some intuition how the meta-analysis should usually work. So in the fixed effect model, you assume that there is some true underlying effect size coming to all of the studies. You can denote them, for example, mu, and you have the individual study effect sizes wise that are normally distributed around the mean effect size with a standard error that corresponds to their sampling variance. So the only difference, so the only reason why the individual study estimates differ from the true value is the sampling variance. And then the second most common model is random effects model, which assume that there is some distribution of true effects of the studies, which is centered at the sum ground mean, and the individual studies are sampled from this, and they might differ because you do some unobserved heterogeneity, for example, different populations, different treatments, etc. And then you sample the true study effects, the thetas I, and then the observed effect sizes then differ from the true individual effect sizes due to the sampling variance. So each study has its true effect size, and this is sampled from some distribution. And you then summarize the mean of the distribution and the between heterogeneity. So these would be the two most common approaches to meta-analysis. So that's the background on meta-analysis. Now you had done basically a half semester course on meta-analysis. Now publication bias. Have you ever, maybe question, have any one of you heard of publication bias before? Okay, so if you summarize it like very briefly, you can summarize publication bias that most large studies are probably published because they are interesting enough regardless of the results. Some moderately sized studies are maybe less likely to get published, especially if they have findings that are not supportive of the expected hypotheses. And then the small studies are probably published only if they have very strong evidence in them. And this creates skew in the literature, at least in theory. And to somewhat prime you how publication bias might look like, I will just show you a couple of hypothetical distribution of test statistics. And imagine you run a z-test with 30% power, and you run it infinitely many times. Then distribution of absolute values of z-statistics would look something like this. So it's some small distribution with most z-statistics between 0 and 2 in absolute values. If we increase power, most of them will just move to the right side. More power, even more. Now you see that only minimum will be non-significant, about 20%. And if you have a mixture, if you have tests with mixtures of powers, for example, if we put 1/3 of these, and these, we'll get a mixed distribution. But the important part of this slide is that all of these distributions in the mixture is smooth. If there were none in absolute values, it would be just symmetrical around 0, and it would be centered, and then we have like much wider mixture. Well, when we look in distribution of test statistics published in journals, for example, on 1 million test statistics in Medline, we don't see anything that's smooth at all. And maybe surprisingly, you will see that there are 2 cutoff points in the distribution that kind of make a valley of missing studies, and these correspond to significant level. So this would be, I would say, quite good evidence for the presence of publication bias. The question is the problem on the individual studies, but does this affect meta-analysis? Because it's the summary of evidence that usually go to when you want to make a decision about something. So if you are a clinician and you are looking at new treatment, you are not looking in the individual studies. You go to Cochrane database, look at the latest meta-analysis, synthesize many of those studies. Well, luckily for us, there was a nice study by Quarren et al. 2020, and they compared 15 meta-analyses with large register replication reports of an effect that corresponded to the main finding. And all of these were based on psychological experiments. So therefore, for example, there are some priming effects, and you can imagine there's meta-analyses, with, for example, 200 estimates, and you have a mechanic estimate. And then later on, there was a big register replication report study, which consisted of, let's say, 30 labs trying to replicate a central finding, and they matched those replication reports and the meta-analysis. And under some assumptions that the effect sizes are representative in the register reports, we would say that the register report estimate should be the best estimate of the 2 effect size, because they are pre-registered and they are reported regardless of the outcome. So the meta-analysis might be a biased estimate of the effect because it just uses the published literature, whereas the register replication report is done and published regardless of the outcomes. So this is come on. This is again. So you had a figure here, and on the different lines there are different meta-analyses. So each line is a different meta-analysis. For example, this is meta-analysis by Oppenheimer et al. On some effect, doesn't matter. And there are different effect sizes, and there are the metabolic effect sizes in red. If you look at the register replication report, so each of these is metabolic estimate. And these are the estimates from the register replication reports. So the corresponding effect then was estimated with a large replication report shrunk towards 0 in this meta-analysis. Not in this one, but it did in this one, and this one, and this one, this one, this one, this one. And in many of those, it basically ended up being 0. So this would be also quite a damning evidence of the effect of publication bias on meta-analysis. So this is quite an established problem that has been studied for a long time. And I'm not the first person to try to do some publication bias adjustment. This field has been alive since 1980s or 70s, and there's been a plethora of method developed to deal with this issue. And I like to split them into 2 main categories. One of them are models adjusting for relationship between effect sizes and standard errors. And I will show one of them just quickly to get some exposure. And they count, for example, trim and fill, fat piece, or indigenous king. And the seconds are selection models of p-values. 3 and 4 PSM models are probably the best known from this, but also there are AK1, AK2, P-curve, uniform, etc. But basically, they always try to model relation between p-values and publication. So that piece, I think it's a nice representative of the model that adjusts for effects and standard errors, and it's very commonly used in practice because it has quite nice behavior in many cases. So that piece is basically a conditional meta regression estimator. And what do I mean by that? It consists of 2 different models. One is called PET, and second we can call one PET, second we can call piece. And one of them adjusts for relationship between standard errors and effect sizes, and the second one adjusts for relationship between standard errors squared and effect sizes. And the intuition behind this is that if we plot effect sizes here of different studies and standard errors of the same studies, and if there is no publication selection bias, then there should be no relationship between effect size and standard errors. This should be a bit more a funnel, but I was unable to create a triangle in PowerPoint to hide some of the estimates. So if you model this relation between standard errors and effect sizes, and this is just a funnel, then the line will be straight. And then the intercept that corresponds to a study with zero standard error would be unbiased estimate of the target. However, if there is some selection, so if there are studies, if small studies with large standard errors are published only if they show very large effects, then the tail of the distribution will go up. And then one possibility proposed by in the PET piece is that you fit a linear regression between standard errors and effect size estimate, and basically are trying to estimate what would be the ideal estimate of a study that has no standard error. And this model is shown to be biased if there is a true effect, because this line will underestimate the effect size if there is an effect present. Or you can fit a piece model. And there I just created a quadratic fit by my hand. You can see it fits very well, and it gets to the correct effect size estimate. And then you have to decide between those 2 models, basically. And how you do that, the rule of thumb is that you first test for the true effect size with PET. If it's significant, that you use piece to adjust for the publication bias. If not, then you use the PET estimate. And then you also need to first decide whether you will adjust for publication bias at all in the first place. So that's the one type of models that operate and on effect size and standard errors. The second ones are selection models. And they adjust for publication bias depending on p-values, as I said before. And they basically just expand the usual meta-analytic model with the grand mean parameter mu. You can also have heterogeneity or not. You have random versus fixed effect model. And then you add some publication bias weights omega. And you define a weight function. For example, here is a step weight function, and you define different steps on p-values, and you estimate the probability of a study being published at a different p-values intervals. And here you can see there's a 3-step weight function, and you set 1 omega to be equal to 1. For example, all significant studies are to be published. And then you estimate the relative publication probabilities relative to the studies that are significant. For example, for marginal significant studies and non-significant studies. This weight function is often quite difficult to estimate if you have only a couple of estimates, because you have to have studies in all these intervals to estimate the weights. And what this weight function does is that it modifies the likelihood of the observed effect sizes or the statistics. So you can see this would be the normal likelihood function F, which would be, if you look at the test statistics, it would be just a t-distribution. And when we weight the likelihood function with the weight function, we will get this cut shape, which maybe reminds you of this cut shape. So that's a good reason why to use selection models for estimating for dealing with publication bias, because it can deal with these cut points. So how does this model perform on real data? So we can look back to the example of Warren et al. And here we also did the estimates of that piece. and 3PSM, which is the two most common adjustments. And here you see there was no publication bias. The meta-analytic effect size estimate and research report in blue are basically the same. And also the different publication bias adjustment methods gave the correct result, because we would want them to correspond to the blue estimate. Just to clarify, the publication bias adjustment method use the meta-analytic data set. So they are done on the same data set as the meta-analysis, and they are just trying to infer what would be the true effect size for which we use the rigid replication reports as an instrument of what's the true value. In other cases, we said that one of the methods perform better. Here, PET-P's, you see, okay, here none of them performs better. Like one of them overestimates, overadjusts, which is PET-P's. One of them does something in between, and so it's still better in the meta-analysis, but they are still quite far from the true estimate. And in some cases, only one of them performs well. So here, PET-P's seems to adjust quite well. The selection models are completely off of the true value. So in different scenarios, the different methods perform differently well. And it's very hard to say a priori which one you should use to model the relationship. Okay, I need to know what's on the next slide because I forgot. Okay, limitations. Yeah, so that was I was simply trying to touch upon is that these different methods has the different limitations, but some of the limitations are quite common. For example, if you decide to use one of those methods, you need to make some decisions. Do you adjust for publication bias or not? And usually these decisions are based on some test for significance. Do you have evidence for publication bias? Those tests are usually quite underpowered. They are based on small samples. So it's very hard to make a very good decision based on those tests. And then even if you decide to adjust, do you use PET or do you use PEAS? Do you use two-step selection model? Do you use three-step selection models? How do you define the cut points on the selection models? And these are all decisions that will influence the outcome of the analysis. Next, you can quantify evidence against publication bias. You can always reject the null hypothesis of no publication bias. And sometimes it might be useful to know, oh, this piece of literature seems to be quite good. Maybe there is no publication bias there, and we can be quite confident about the results that we observe here. Most of these methods are under high heterogeneity. So if those studies differ a lot, and they are sampled from some distribution, then the methods tend to perform much worse. And they have often convergence issues, especially in very small sample sizes. So these are fine. So these are the major limitations of those publication bias adjustment methods. And it's also the reason that if you look at the published literature with meta-analyses, quite often they just use a funnel plot to look at the data and say, oh, there's no publication bias, and they don't want to deal with publication bias adjustment because it's very hard to decide what you should use. And also it's very hard to estimate those models, which are also usually not very accessible to people who are not skilled in R, etc. Which, to be fair, like most practitioners who run meta-analyses and play data are not programmers. So this is a thing that we try to address with our method, with robust Bayesian meta-analysis. And in a nutshell, screw me. We use, in a nutshell, I don't remember this slide. We use Bayesian model averaging. We use Bayesian model averaging to combine different models that you can fit. So we look at different ways how to adjust for publication bias, or even not to adjust for publication bias. And instead of deciding one of those models you should use, we fit all of them. We look how well the data are aligned with the models, and we use Bayesian model averaging to draw inference based on all of the models simultaneously. Then, because we are in the Bayesian settings, we use Bayes factors. So we can quantify the evidence in favor or against depends on the effect, heterogeneity, and publication bias simultaneously based on the whole model ensemble. We use prior distributions on some parameters to regularize them and to help with the fitting issues, which is very difficult in the frequency settings. For example, if you have the Bayes function, we can define it to be decreasing. So the larger the p-value, the lower the quality of study being published. And just this simple regularization makes the behavior of the models much, much better. And because if you're in Bayesian setting, you don't have to deal with the sampling plan. So theoretically, if you are a purist and you think about meta-analysis, you cannot get the p-value from it. Because if you go to meta-analysis, there is no defined sampling plan for the studies that have been conducted. And then if you collect more studies, then or if more studies are conducted, then the sampling plan that you might have thought about is again destroyed. So basically, if you want to do meta-analysis, you cannot do it in other way than a Bayesian way from theoretical perspective. So how does Roma-verse conceptualize Bayesian model averaging? There is a nice figure from one of the papers in our lab that we use. We actually have an illustrator that we pay to create figures for our papers. Super nice touch. I highly recommend. And this is taken from paper with regression, so I will modify it a bit. You can imagine that you have different demons, which represent different assumptions or hypotheses about data you might have. So in the meta-analysis thing, you might have models that say, oh, there's the treatment effect works. So you can have assumption about the presence of the effect. You can have, then the opposite assumption is there's no treatment effect. So the null hypothesis of no effect. And similar with heterogeneity, you can assume there's the presence of between study heterogeneity versus there's absence versus there's presence of between study heterogeneity. And then also we can define assumption about publication bias. So there's no publication bias or there is publication bias. So each of these demons represents one of those assumptions about our data generating process that we might have. What we do with those demons, with the models, we feed them with the data. And if their taste was aligned with the data, they predict the data well, they will grow. And that's what we do. We just listen to the models that predict the data well, grown, and speak louder. So we only wait. So basically, when we are looking back at the model ensemble, we weight our decisions and our opinions based on how well the models are aligned with the data. So in slightly more detail, because I am at the stats department, this is the equation slide that you've been waiting for. You can imagine, just like simplify to two cases, two models example for now. So we have a model that assumes there's presence of the, and one thing. I combined some of the slides from different presentations, so the denominator, the symbols and stuff are not going to be consistent throughout the talk, but I think it's still be understandable. So you can imagine you have two different models. Models assuming absence of the effect, and model assuming presence of the effect. And it's just fixed effect meta-analysis. So there's only one parameter here, which has some power distribution f, and there is the one parameter is set to 0. And that's how we specify the models assuming absence of the effect, presence of the effect, and assuming there's no between study heterogeneity and no publication bias. Okay, so we have the parameter distributions here. We have the likelihoods of the models, and then we collect data, and we feed the models with data, and we update them with the models. So we get the posterior parameter distributions by just the simple Bayesian updating, which we need the marginal likelihoods for if we want to have a non-proportional. But we also use the marginal likelihoods to get the posterior probabilities, which we needed to define. I am missing the definition of it. So basically, we also need to define the primary probabilities so we can update them to the posterior model probabilities. And then in the next step, we just want to draw inference. So we use all of these updated models and posterior distributions and posterior model probabilities to summarize them with Bayes patterns, where we just look at how well the different models predict data, which we can also conveniently, for later purposes, summarize as a change from the prior odds to the posterior odds for different models. And then for the model average posterior distributions, when we just combine the posterior distributions from the individual models by the posterior probabilities of the different models. So this is basically just the whole setup of Bayesian model averaging. And if we have more than two models, then we just combine those models into sets based on the inference we want to draw. So if we want to draw, for example, inference about presence of the effect, and we have versus absence of the effect, and we have multiple models, and some of them represent models assumptions about absence of the effect, and we group them together, sum their prime model probabilities and their posterior probabilities, and look how they differ from the models assuming absence versus presence, and we get the Bayes factors that are model average across the whole model space. And similarly, if we want to get posterior distributions of some parameter across multiple models, and we have more than two models, we just average across all of those models in the posterior distributions that we have. So it's just quite straightforward generalization from two models to multiple models. Okay. I'm doing something. Well, that's great. So we have different model types, and we are trying to get some model average estimate, for example. And to just reiterate this very quickly, we can divide them by the assumption about absence or strength of the effect. So if we put the total posterior probability, the primal probability, we can split it half-half. We must make absence of the effect, or strength of the effect. And we add the assumptions of heterogeneity. We just add another split in the tree. And let's say we assign half of the primal probabilities of models having absence of the effect, to the model having absence of the effect, and absence of heterogeneity, absence of the effect, presence of heterogeneity, presence of the effect, absence of heterogeneity, presence of the effect, presence of heterogeneity. So we have 4 models. And this is just how we can split the probabilities to different models. And this corresponds to Bayesian model average meta-analysis that has been done in our lab before. And how we extended with Roma was that we just did another split. So we added assumption about the publication bias, and we split all the model probabilities one more time based on the present versus absent publication bias. So in the end, you have 8 different model types, each with different prior model probabilities. The thing is, like in this figure, you just see some models assuming the presence of the publication bias, but there's only one endpoint. But as I said, there's many more models that can be used to adjust for publication bias. So what we do, we just look at this assumption about the presence of publication bias, and we just split this daemon into many more smaller assumptions. So basically, you can think about daemons all the way down. And here we define assumptions about different ways how the publication bias might operate. So just in a straightforward way, you can extend this Bayesian model averaging process from the different assumptions to different ways how the assumptions are represented. So here, for example, we can define some bad models, or we can define a different relationship between FXA standard errors, or different weight functions. So the publication bias may be on one-sided selection, on significant p-values, or two-sided selection, etc. So, and also the direction of the effects, etc. So there's a lot of way how you can specify these publication bias adjustments. And if you look into the different ways that we employed in ROBMA, then we have 2 models for the adjustment correlation between effect bias and standard errors, which would be the PET and PEACE model. And then we define 1, 2, 3, 4, 5, 6 different weight functions that we thought are the most plausible explanations, or like the most plausible assumptions about publication bias operating in real studies. So either two-sided selection of significant p-values, so you don't mind about the direction, whether it's significant, it's selected with higher probability than if it's non-significant, or maybe also marginal significant p-values, or maybe there is also a role whether the studies are in the expected direction of the effect form. And this just makes the different ways how you adjust for publication, like how you can adjust for publication bias. So in total, there is there are assumptions of the presence or absence of the effect, which is 2. Assumption about absence or presence of the origin, this is by 2. So that's 4 different model types, plus 8 ways of adjusting for publication bias, 1 way of not adjusting for publication bias. So it's 36 models in the whole Bayesian model average ensemble. And this basically covers these models that are most commonly used. The reason why we didn't cover this one is because it discards data, and you cannot get marginal likelihood when you discard data, or you impute data. This wasn't published yet, and these 2 just suck. Don't use those. I hope you don't have friends there, but seriously don't. So back to the example with the meta-analysis and recent replication reports. Here again, in this case, you see that the bad piece and selection models perform quite well, and our ROMA estimate is just slightly lower than either of those, but I would say still acceptable. If you look here, neither pet piece, neither selection models adjust well, but our Bayesian model averaging gets much closer to the true value. But for example, here, the pet piece seem to get the answer correct, but when we average, we are further away than would be the single pet piece system. So this also shows that even though we do most cases better, It's still statistics, no magic, and we can still get the correct answer some of the times. And to trust me that we do better on average, I also have a table with numbers. Yes, I do. And we can evaluate the different methods with different metrics. For example, our estimation factor, how much higher the estimate is on average in a publication-based adjustment versus the replication report, bias, or RMSE. And when we compare to the two methods that I was describing before, we can see that we have better bias and we have much lower RMSE. And this will be basically the main finding across all our papers, that what improves the most is RMSE by Bayesian model averaging. The bias doesn't always get much better. In this case, it did quite a lot, especially from the selection models, but RMSE decreased by quite a large margin. So this is a nice example and illustration that I just like to use because it's like relatable, but it's 50 meta-analyses. So it's not real proper evaluation of methodology. And for this, it's good to run a simulation study. And that's what we did. And we found this paper by Honk and Reed, published right when we were writing our paper. And what they did was super nice. Okay, one thing I should have thought about the publication-based adjustment literature. As you saw, there's a lot of methods and a lot of authors who publish there. And each of them have their idea how publication-based works. They develop their method and they develop a simulation study that matches the method because that's how they believe it operates. So it's not only that they would say that they want to bias their method, but they just make simulation studies that correspond to their beliefs about publication bias, and they make corresponding methods. So surprisingly, the people methods perform best in their simulation studies. To address this issue, these two authors collected 4 simulation environments from different authors that were published here. And they compared all these different methods across those simulation studies. So you can think about this, it's kind of balancing the weights because different people have different methods at play and different simulation environments. And either the methods should perform good across all of these simulation environments. And this was around like 1620, 1680 conditions across all the simulations. So it was quite a large simulation study. If we just quickly look on average performance across all environments with the different methods, you can see that we did quite well, actually. So if you look at the bias and RMSE across the simulation environments, it's quite consistently up at the top, which was especially nice because the finding of the original study, when they compared all these methods, the authors, the Honk and Reed, they didn't use our method. So they just used the methods that were available at that time. So they extended their simulation study with our method and added to their results. So their finding was that different methods perform quite inconsistently across different environments. And some of them are very good somewhere, or are good at bias, are very bad at RMSE, etc. So we are quite happy that we got quite a consistent performance across all the simulation studies, if we just average across the performances. But we also found that if you look at the different environments, then especially in one of them, we had much poorer performance than the other ones. And it was the Crowther and colleagues simulation environment, which one is environment based on psychologists. So we basically failed in our environment because this one was more like medicine based, this was more like economics, this was econ/medicine, this was more psychology, and we failed in that one. But if we failed in that one, we found out that 2/3 of the simulations has not only publication based but also p-hacking. And when there is a lot of p-hacking in the simulations, it modifies the likelihood even more. And then the models are just very misspecified. And all of them are misspecified. So even if you model average across a lot of models, but all of them are very wrong in terms of how the likelihood works, then we still ended up with quite large bias. I think this is absolute bias. And if we look in the simulations, and we found that basically if there is a lot of p-hacking in the simulations, then we tend to underestimate true effect. And that was the same for MSC. So this is the methodology and how it performs. But one of the important pieces is how you can also run it. Because when I show this slide, I think no real researcher would be willing to use this and implement this by them. So this is the usual researcher trying to run our method based on descriptions in the paper. They are not very heavy. So we implemented it in R, and basically what you do, you just do library roadmap to load the package, and you fit the model as you would do any other meta-analysis. Just with FXI standard errors, you can use summary, and it produces some summary of the object. So there's a summary of the model components across all 36 models. And you see that in this example, there is quite strong evidence for the presence of publication bias. There's evidence against heterogeneity, and there's very weak evidence against presence of the effect. And you also get the model average estimates for all the different parameters. So the effect size, model average effect size estimate is somewhere between 0.5 and 0.21, minus 0.05, etc. And then you have all usual convenience functions you would have in R. So you can plot the posterior distribution, which is a combination of the spike and the slab, because you have models assuming absence of the effect, presence of the effect. You can also do the ggplot. You can add labels. You can look only on the conditional distribution, assuming there's the presence of the parameter. For example, here you omit all the parameters, all the models that assume that tau is equal to 0. So you get only lessons from random effect models, etc., etc. And one thing that I really was very happy when I was implementing the package, I really wanted to make it quite general. So if you want to play around, you can specify different prior distributions for the effect. So do you want a one-sided test? You can just specify your prior distribution and truncate it at 0. Do you want to have it non-centered at 0? Just increase its mean. We don't have non-local moment priors yet. I know. And the same with the publication bias, etc. You can specify quite a lot, and the package is very flexible. And because not everyone is able to run R, then we also added to JASP. And then you can play around, and if you really want, you can also specify all these different things, so prior distributions, by just looking at the menus. You can specify any of those distributions that you might want. It gives you overview of the models, and when you fit them, which might take the time, especially when you run it in JASP, because you cannot use multi-threading. You can look at the estimates, at the tables, etc. So that was the methodology, and I have found 12 minutes. So I will just show some examples of applications. And that was done with much larger group of colleagues that we worked on different examples and different things. So I think one of the most interesting one is Minos nudging, that was quite famous when it was published, because nudging is actually quite a big thing in behavioral economics. And as a psychologist, when I was asked before 2022 what's a good example of research that psychology is useful, I would say nudging, and framing, etc. It's used in real life. There's a lot of studies, a lot of evidence, and that's what we taught. So this meta-analysis collected around 440 estimates with more than 2 million people. And the conclusion of the study was the choice architecture, aka nudging, is an effective and widely applicable behavior change tool for facilitating personal and socially desirable choices across behavioral domains, geographical locations, and populations. So not only it works on average, but it works everywhere when the studies were conducted. And it was like widely celebrated paper news published, basically showing huge evidence for nudging as it's used. And it's used in econ, for example, government interventions, etc. Like US government is whole agency develops programs based on nudging theory. And they said that there are several like moderate publication bias towards positive results in literature, but they didn't deal with it anymore. And there's one sentence in the paper: if they were to assume that the publication bias is severe, and they did some robustness analysis, the effect would decrease from around 0.4 to 0.08. But they just completely omit in their discussion, in their abstract, etc. So when this paper was published, we saw it on Twitter, and we saw this figure that was attached by the authors to show how many studies and how well they look like. But if you can read funnel plots, here you have standard errors of the different estimates, and then you have effect size estimates. So if there was no bias, there was effect, then you would see this triangular shape with smaller studies just have more imprecision. But you see that all of those studies are flying towards the right side. And there's also some suspicious studies with effect size around 3 that are clearly fine. Okay, we are recording. I am backtracking what I said. There is some people suggesting that some of those studies might be fake and the data are not alleged, because some people get sued over those studies actually. So what we did, we analyzed the data with our method, and if we look at the overall effect size estimate across all of the studies with the Bayesian model averaging, that we find base factor around 0.95 in favor of the absence of the effect. So basically the models are 1-to-1, so there's no evidence after we adjust for publication bias. And also the effect size estimate when we average across all the models is basically from 0.0 to 0.40, which is quite a huge change from around 0.40, which was the original reported estimate. And when we look at the different domains, that we see that in some of the domains, actually, we have quite some evidence for the absence of the effect. For example, in the health domain, or especially in the financial domain, or pro-social domain. So it seems like if you are carrying up with your finance, then nudging is not going to do anything to your decisions. And also we looked at the different intervention categories, which maybe the structure seems to have some evidence for, and there's huge heterogeneity. So, well, the estimate is quite uncertain, but we also find quite a lot of heterogeneity among different domains. So there are probably some intervention that works, but there's also a lot of interventions that do not work. So you cannot approach nudging just with a blank state, everything works, we can do whatever, but we need to look in much more detail what actually works and what does not. And we are not the only one who realized the data. So there were another teams who submitted a commentary, and their conclusions basically were very similar to ours. I will just let you read, and I will try to get a sip. Sorry, so in this case, the problem was so large that whatever you use, if you just tried to adjust for publication bias, you would get very similar as we did. So that's kind of satisfying that we are not demolishing a whole field based on one method that we just developed, but that also other people kind of agree with our conclusions. So I will skip this example because it's just the same thing over and over again. And I will talk very briefly about publication bias and publication. So I will throw in the joke. So I showed you publication bias adjustment methods, and I showed you some examples when they perform quite well and they perform much better. So that's how we deal with publication bias by publication bias adjustment. But what if I'm making publication bias in the publication bias adjustment literature by selecting examples to show that my method works, and on examples that show that there's publication bias? Well, we can just look at large set of meta-analyses, and we can try to adjust all of them and to see how does publication bias behave, or like what's the evidence for publication bias in large, hopefully more or less random sample of meta-analyses in the literature. So there's one study published in Psychology quite recently that it's something very similar. They collected around 433 meta data sets, and they applied different methods for publication bias adjustment, and they used some model selection techniques to select one of them based on simulations that were done previously. But there are many problems with this approach, and that's you have to kind of assume some of the things of literature versus you have to assume is there heterogeneity or there's no heterogeneity, and how severe the publication bias is, because you cannot use the estimates of different publication bias methods to select the category in which you are, because those methods are biased under different categories for all of their estimates. So you kind of cannot know which methods you should use before you use them, but when you use them, you don't know whether their results are reliable if you do model selection based on those diagrams. So they assume 4 different possible scenarios for all of the papers, and they did a model selection according to them. These are scenarios, and this is of course the thing that we don't need to worry about when we use FrogMath, because we just fit all of the models and we weigh them by their predicted performance. And what they found when the study adjusted this whole set of foreign metallic data sets, they found there's like minimal downward adjustment, and basically the title was there's small or non-publication bias in meta-analysis and psychology. And the largest bias that they like on average they found bias are approximately about 0.032 in coherency, so it's very, very small. And if you look in the bias estimates, or like there's a difference between the original effect size and the adjusted effect size in correlation coefficients. And 0 would be there was no adjustment. And if it's lower, then the adjustment was higher than the original estimate. But if you look at those corresponding estimates in these categories, you see that they are basically just random spread. And some adjusted upwards, some adjusted downwards, and across all 4 different scenarios. So this will be the results with the traditional methodology. Okay, well, can I go forward? I will go backwards. Well, so then we ran the data set with our Roma method, and we did 2 things. We looked first on the evidence, so we computed the posterior model probabilities or posterior probabilities for the presence of the effect without adjusting for publication bias. So that's on the x-axis. So here you see the marginal probability. Most of the meta-analysis would find evidence for publication bias. And then we compare to the models adjusting for publication bias. Also, and this is the marginal probability of that. And you can see that there are basically 3 different categories. There are a set of models that basically don't change when you adjust for public of data sets that basically don't change when you adjust for publication bias. There's huge amount of meta-analysis which evidences decreases a lot when you adjust for publication bias. There are those 4 different meta-analyses that you might be like puzzled, like what the hell is happening here? The thing is that we adjust so much to the different direction that we find evidence for the effect on the opposite direction than the original meta-analysis. And then there's a lot of studies in between that are adjusted to different degrees. And then we also looked at the effect size estimates. So from the different meta-analysis. So if you just use default random effects model without adjusting for publication bias, it would be the proper density. If we use Bayesian model average meta-analysis without publication bias adjustment, it becomes slightly smaller because it also model average across null models, so it does some shrinkage over 0. But then the publication bias adjustment in trauma shrinks it even more for many different studies. And then you can see the difference of the different densities that are there. And yeah, or you can look at the differences from the effect size estimate. Do I this figure? Yeah, this was the figure I thought I would have had there, but it was 5 slides later. So if we look, this is the original results when they look at the different model selection criteria according to different models that basically just adjust up and down, right? It kind of seems like a random noise added to the data. And this is the publication, but this is the adjustment when we adjust with robust Bayesian meta-analysis. And when we compare either to the frequentist meta-analysis or to the Bayesian model average meta-analysis. And actually, there's a huge proportion of studies that are adjusted by a very small correlation coefficients. And then there are some that are adjusted much more. And I think, I don't remember the numbers, but I think it's like 40% of meta-analysis that are adjusted by less than 0.05 in correlation coefficient, and then others that are adjusted much more. So, and we also did another study when we get much more meta-analysis, and I will just show you one result, and I will finish the presentation. So we collected around 70,000 meta-analyses across medicine, economics, psychology, and analytical sciences, and we did basically a very similar setup. And here you see distribution of posterior probability for presence of the effect without publication bias adjustment in medicine. So there are a lot of studies that actually already show evidence against the effect or meta-analysis in medicine, which is kind of good to know because it seems like that there are meta-analyses showing, oh, this treatment doesn't work, even before adjustment. But if you adjust, then the probabilities shrink towards 0. So the proportion of meta-analyses that would have evidence for presence of the effect decreases to some considerable degree, but it's not that too bad, I would say. Why I would say it's not too bad? is because when we look in economics, psychology, and environmental sciences, it's just ridiculously bad. I think in econ, the median posterior probability went from 0.99 to 0.37 or something for presence of the effect in the meta-analysis. Psychology was slightly better, environmental sciences slightly bit more better, but yeah. And similar with the bias, etc. So just to sum up, some advantages of the robust Bayesian meta-analysis is that it can incorporate uncertainty of different models. So you don't have to select them, but you can do Bayesian model average across the different publication-based adjustment methods. You can provide evidence for a null or the alternative because you are using base vectors. It has better performance with small samples, and you can incorporate expert knowledge with prior distributions. But it also is slow because you require FCMC sampling. So if you have a data set with 200 estimates, you will not fit all 36 models, and you don't do it parallel, it can take like 6 or 7 hours. On the other hand, you already spent 5 or 6 months collecting primary data from the literature. So you shouldn't be too fuzzy about waiting one night to get the middle estimate. And it can also fail under strong p-hacking. So if there's not only publication bias, but also p-hacking, then all of those methods just perform much worse. And our method will tend to underestimate the true effect. Some thoughts, what we are working on next currently is adding meta regression, or well, we actually just added the meta regression. So we can actually use this original slide with you need only this predictor, or there's more predictors to moderate the effect, or maybe no predictor. And then you just extend the whole model ensemble with additional steps, which is adding different model assumptions on top of your different models. If you have 2 predictors, or if one predictor, you multiply the number of models by 2. So it's basically 2 to the power of number of predictors by 36. But we are also working on some sampling procedure that will sample across the model space, so you don't actually have to estimate all those models. That could simplify it a bit. And then you can specify a meta regression, so you can specify different predictors, and you can put different power distributions on all of them. So again, it's highly modifiable, and also it's non-zero. And then we're trying to work on multi-level, multivariate models, imputation, mixtures, but that will probably take still some time to develop all of these remaining things. And maybe just better thing than adjusting for publication bias would be not to have publication bias in the first place, because all of these things are just plasters that you put on your wound, but it doesn't really solve the problem in its core. And that's just we need to do better studies, and we need to make sure that the good studies are published, that all studies are published, and we have some comprehensive view of the evidence. So thank you for your attention. There are links to the package or to JESP, and there is a stat scheme that I like a lot.
It seems that the p-values and effect sizes to the published, there's a dynamic process with that, right?
Yes.
So there's a paper that comes out, publishes some unexpected finding, and the publication bias to the subsequent papers is different.
Also, there's also temp for dynamic to the whole process. Yes, I think so. And there are some meta epidemiological studies that look also on the publication year in the sequence. If you meta-analysis, how does the publication process change for the different things? And the usual finding is that the first study has the highest estimate of all of the studies that are done, and the effect is decreasing over time. There are also like different explanations you can have for this than just this. For example, the first study is just using very like the biggest possible treatment that you could have, and you can look at the different sub-treatments that are more specific and have maybe smaller effects. But I think it plays a large role. But I think on the individual meta-analysis, like you can estimate those things if you have large data set with collections of thousands of meta-analysis and primary studies. But I just think for this on the individual meta-analysis level, it's very difficult because already just running, if you look at some of the selection models, they have like 6 or 7 parameters. The likelihood is discontinuous, and some of the parameters change the likelihood. And you have 10 studies to estimate those models. And then still adding another parameter that would deal with this. I think it's already very challenging. It will be interesting to try, but it would be an interesting way forward maybe at some point. Yeah.
Are you able to use information? So often people publish studies, they don't publish one p-value, they publish a whole bunch. They make the space, you know, incorporate the other p-value. You know, how you might get up into it.
Yeah, that's a really good point. And we've been thinking about this recently. And you could specify a different vector. You could specify a vector of effect size, standard errors. I'm not sure that currently in this version we also have an option to add a different vector of p-values. I think maybe now we are just computing the p-values based on the effect sizes that are put as an input, but you could also supply a separate input of p-values that would work as the categorization threshold for different ones. So it would be a way that those ones could be also extended. But I've seen this done recently in one paper, but we try to keep it quite equivalent with the usual selection models that are in the literature. But you could definitely extend it in this way. And I think for the best reason for doing this is if you have medicine and some of the estimate, and you have binomial, you have table, a frequency table, and you can transform the effect size estimate to log odds ratios, etc. And the mean answers are done at the same effect size estimate. But the original studies might have been published with the estimate on log odds ratios or risk differences. And then you get different p-values based on different effect sizes that you may use. So it would be, for example, one very nice way to do this. Thank you. Yes.
Nice presentation, good summary of work. My question is very basic. For one methodology, what is the most popular or reliable method?
So you mean what's the most commonly used mathematical method, basically combining evidence from multiple studies right now?
No, just one thing.
Yeah, I think the most commonly used is random effect beta analysis still. I think it's a default choice different default choice in medicine. Unless you have very small samples and you have frequencies, then they use something that's equivalent to fixed effect beta analysis. In economics, they like to use unrestricted weighted least squares, which is very similar to fixed effect models, but with multiplicative heterogeneity. And in psychology, the default method would be also random effect beta analysis. So from these three fields, usually random effect analysis would be the default option they should use, which is without complication by suggestion.
On this situation where one could have access to the original data,
but I mean, the data that you have from the analysis are the original data that you have access to. What you maybe mean is the data from the unpublished studies that might have been or conducted but are not published. And some people try to get access to unpublished studies, and if you do search for data in meta-analysis, you also try to do some shadow literature search to find the unpublished results. But usually you don't find that many of them. So unless you have very good connections with all the researchers in the field, and then also you need to know all the researchers in the field. But if you think about it, like the people who have multiple studies that didn't end up being significant and couldn't publish them, they are most likely to leave academia because they have 10 papers in their file drawer that they can publish and they can advance in their career. So you cannot even get in touch with those people. So like the best comparison in this regard, I think, is comparison with the research reports, which is the current example. And otherwise you can do simulations to have the ground truth right.
what is the view in psychology or social science about meta-analysis or combining?
Like if you are in science class and you are doing some domain specific learning, then the first thing that you are being forwarded to is a meta-analysis, because there are hundreds of studies on different topics. So usually people know some landmark paper that establishes a phenomenon, and then you look at the meta-analysis because it summarizes the evidence across all of those studies. And also it usually does some meta regressions when they look at how does the effect vary to some conditions. And if you were to do it yourself, you basically have to redo the whole meta-analysis in your head, read hundreds of papers. So basically the meta-analyses are used as just a summary of a different field. And the same for medicine. So even you are like, if you are going to FDA and you want to establish new drug, you of course need to have, you have 2 trials rule and you need to register the trial, etc. But then over time there's accumulation of trials, and usually like clinicians, and they are saying between 2 treatments that have been approved, they look at, for example, Cochrane database of systematic reviews, when there are meta-analyses combining different studies for the same treatment, etc. So I think like from practical perspective, it's like the go-to thing. And then you could argue, well, maybe you shouldn't use meta-analysis at all, because I have shown they are biased, right? But what you do is that you go to the individual studies that are even worse, because the meta-analysis is just aggregation of different studies. So there's like no other way you can do unless you decide to, oh, let's forget everything that's been done and start from the blank slate. And then what's the thing next, right? We can go back to using bloodletting to treat the fever because we think it's good, and we have no evidence.
Right, I think the speaker again.